Hello everyone, and welcome to this presentation, Oscilloscope Probe Fundamentals. In this presentation, we'll go over the basics of oscilloscope probes, including the most common probe types, as well as explain how to choose an appropriate probe for a given measurement application. This presentation is divided into 6 sections. The first is a general overview of probing and the things to consider when deciding which probe to use. The next covers passive probes, which are the most common type of oscilloscope probe. We'll then talk about probe compensation and why this is important when using passive probes. After that, we'll switch to current probes, since these are another very common type of probe. And we'll end the presentation by talking about 2 special types of probes: differential probes, which measure voltage between any 2 arbitrary points, and active probes, which can be useful when making challenging voltage measurements. Let's begin with a general overview of probes. Probes are the most common interface between an oscilloscope and the measured signal, although in some applications a direct cable connection can also be used. There are many different types of oscilloscope probes, and we'll cover the most important of these in this presentation. One thing that's important to keep in mind is that oscilloscopes natively measure voltage, and this voltage is usually measured with respect to ground. You may hear this referred to as a single-ended measurement. And therefore, special types of probes are needed to adapt or convert other types of signals into a form that can be measured by the oscilloscope. But for all types of probes, there are 2 important characteristics, namely bandwidth and loading. Let's take a quick look, therefore, at both of these characteristics, starting with bandwidth. Like oscilloscopes, probes also have a bandwidth that's part of their specification. This is the frequency range over which the probe can accurately measure amplitude, and this is quantified as the frequency at which the measured amplitude is 3 dB, or about 30%, less than the true signal amplitude. When choosing a probe, a good rule of thumb is that the probe bandwidth should be at least 1.5 times the necessary scope bandwidth. That is, if we need 1 GHz of scope bandwidth for a given application, we should choose a probe with 1.5 GHz of bandwidth. Having greater probe bandwidth also means more accurate measurement of the signals within the so-called flat frequency response region, and this in turn can increase overall measurement accuracy. Next, let's look at probe loading. Ideally, an oscilloscope probe should not become part of the circuit under test, and also should not distort the measured waveform as seen on the oscilloscope. However, if the probe has a low input impedance, it can load the circuit. This means that current flows into the probe, causing the measured waveform to become distorted. In addition, loading may cause the behavior of the circuit to change when the probe is attached. Loading due to oscilloscope probes is primarily due to the probe's capacitance, and therefore capacitance is a key probe specification. If a probe has an excessive amount of input capacitance, this will distort the signal. Higher frequency components become attenuated, and this attenuation will affect the amplitude and the shape of the measured waveform. Another important probe-related topic is channel input impedance. Some oscilloscopes allow the user to select between a 50 ohm and a 1 megaohm input impedance or termination. This is configured through the scope interface on a per-channel basis. The standard impedance for an oscilloscope input is 1 megaohm, and this is the proper setting when using passive probes. The optional 50 ohm termination is most often used when probing with so-called active probes, or when directly connecting to the channel using a BNC cable. Many test and measurement instruments and RF devices use 50 ohms as their standard termination. It's important to choose the correct input impedance, since the wrong input impedance can affect the measured signal amplitude. For example, seeing twice the expected voltage when the termination is set to 1 megaohm instead of 50 ohms. In addition, the maximum safe input voltage is often much lower when the termination is set to 50 ohms instead of 1 megaohm. Some scopes don't have native support for a 50 ohm termination, but in this case, special feed-through adapters can be used, when needed, to provide a 50 ohm termination. Now that we've discussed these general points, let's start looking at different probe types, beginning with the most common one, namely passive probes. As the name implies, passive probes are passive. That is, they have no active components, and therefore they can operate without power from the scope. Passive probes are extremely common, and a set of passive probes is often included when purchasing an oscilloscope. Moreover, passive probes are usually interchangeable between scopes, even scopes from different manufacturers, although passive probes from different manufacturers will often have different performance and other characteristics. Passive probes have many advantages. They're relatively inexpensive, they're rugged, and they're easy to use. In many cases, the user can simply connect the probe to the scope, attach the ground lead, and begin probing. Different passive oscilloscope probes may have different attenuation factors. These describe how much the probe attenuates the measured signal. The most common factors are 1x, 10x, 100x, and 1000x. Note that these are pronounced and written in different ways. Some people would call these 1 times, 10 times, etc., or write them as x1, x10, etc. 1x and 10x probes are the most common, but 100x and 1000x are often used for making higher voltage measurements. Although it should be clear that higher input levels require greater probe attenuation, attenuation factor also affects things like loading and bandwidth. Lower attenuation leads to greater circuit loading and lower bandwidth, both of which are usually undesirable. On the other hand, lower attenuation does also usually mean lower noise. In order to correctly display voltage values, passive probe attenuation must be configured on each scope channel. This can be done manually through the scope's user interface, but in some cases the scope can detect whether a probe is 1x or 10x and adjust or configure the channel settings automatically. This is done by means of a small metal pin on the scope side of a 10x probe, that is, near the scope's BNC connector. A sensing ring around the channel input impedance can detect this pin and thus determine when a 10x probe is attached. Note that this method generally is only used to distinguish between 1x and 10x probes, and cannot be used for probes with higher attenuations. Most probes have a fixed attenuation factor, but there are also switchable probes that allow the user to choose between 1x and 10x. This is done by means of a small switch on the body of the probe. The position of this attenuation switch can't normally be sensed by the scope, so when using a switchable probe, the attenuation factor must be manually configured by the user. Although these types of probes offer additional flexibility, for a variety of reasons they're more common in hobbyist than professional scope applications. Let's spend a few minutes looking more closely at 1x and 10x probes. A 1x probe simply connects the scope to the test point without any additional attenuation. As mentioned previously, this means that 1x probes have high sensitivity and can see small signals more easily. A 1x probe, therefore, is useful when the signal level is low, say less than 1 volt peak to peak. 1x probes are also suitable for low-frequency applications. A 1x probe has low bandwidth because the input capacitance of the scope acts as a low-pass filter. This means that a 1x probe can be used to reduce or eliminate high-frequency noise that's riding on top of a lower-frequency signal. The standard 10x probe supplied with most new oscilloscopes reduce signal amplitude by a factor of 10. This is done by incorporating a 9 megaohm resistor in the probe tip, and this resistor then acts as a voltage divider, together with the scope's 1 megaohm input impedance. Higher attenuation makes 10x probes good for higher voltage measurements. The added attenuation also increases the scope input impedance by a factor of 10, meaning that 10x probes create less circuit loading than 1x probes. And recall that 10x probes have much wider bandwidth than 1x probes. This is because the capacitance in the probe tip helps to cancel out the scope's inherent input capacitance. This is particularly important when measuring signals with high-frequency components, such as square waves and pulse signals. One last thing to keep in mind about passive probes is that they are single-ended. That is, they measure voltage with respect to ground. This ground connection is usually made via a ground lead attached to the probe body on one end and to ground on the other, often by means of an alligator-style clip. It's important to keep this lead as short as possible, since longer ground leads add inductance to the measured signal. This added inductance affects higher frequency components and can create ringing and over- or undershoot in square wave or pulsed signals. Note that when a ground point is available near the measurement point, a slip-on spring-style ground lead can sometimes be used to minimize the length of the ground connection. Before we move on to other probe types, let's spend a few minutes talking about probe compensation and why it's important when using passive probes. As we discussed a few minutes ago, passive probes contain both a fixed parallel RC network in the probe tip, as well as a variable compensation capacitance, usually at the scope attachment point. Probe compensation is the process used to adjust this variable capacitance in order to cancel out or compensate for the inherent input capacitance of the scope. Properly compensating passive probes is important for obtaining the best possible accuracy and/or linearity in measurement results. Let's look at why this is. A poorly compensated probe causes two main types of measurement inaccuracies. The first is incorrect amplitudes. For example, if we compare a measurement made with a properly compensated probe to measurements with an undercompensated or an overcompensated probe, we find significant amplitude variation even at low frequencies. The second consequence of incorrect probe compensation is distorted waveforms, more specifically, changes in the rise and fall times of pulse signals. It's important to remember that these inaccuracies increase with increasing frequency, and thus probe compensation is more important as the frequency of the measured signal increases. Note also that different oscilloscopes will have different input capacitances, and therefore probes need to be recompensated when moving them to a different scope. So, how do we compensate a passive probe? Most oscilloscopes have a built-in 1000 Hz square wave generator for probe compensation. Square or rectangular waves are used for probe compensation because they have both high frequency and low frequency components. The probe tip is connected to the signal source, and the probe ground lead is connected to ground. The oscilloscope is then configured to display the probe compensation output. A non-conductive tool is inserted into the small hole in the probe compensation box, and this tool is rotated in order to adjust the probe's capacitance, such that the displayed square wave is as rectangular as possible. A passive probe is properly compensated when the tops of the displayed compensation signal are essentially horizontal. Overcompensated probes create overshoot on the leading edge of the signal, and undercompensated probes cause undershoot on the leading edge. As mentioned a moment ago, probe compensation is nothing more than adjusting the compensation capacitor until the displayed compensation waveform has rectangular edges. Note that this usually takes only a small fraction of a turn. Like most oscilloscope probes, passive probes measure voltage. The next most common type of probes are current probes, which are used to measure current. All oscilloscope probes share one common characteristic. They provide a voltage at the scope input. Recall that the primary function of an oscilloscope is to measure voltage as a function of time. Therefore, a logical question would be, how can we use oscilloscopes to measure current instead of voltage? Since oscilloscopes only measure voltage, we need to convert measured voltage to a current in an accurate and predictable way. For example, we could come up with a scheme whereby 1 volt at the scope input would correspond to a measured current of 1 ampere. There are two main ways that scopes are used to measure current. One of these is by using a so-called shunt resistor. Here we measure the voltage drop across a very low-valued resistor, typically single ohms or less, and then use Ohm's law to calculate the current passing through it. This often requires a special type of probe called a differential probe, something we'll discuss later in this presentation. The other method, and the one we'll discuss on the next slide, is using a special type of probe called a current probe. Current probes are a non-invasive way of measuring current. That is, they don't require the circuit to be broken. Instead, these probes are placed or clamped around a conductor. Current probes work by measuring the electromagnetic field created by current flowing through a conductor, and then mapping this to a voltage using a known ratio of volts per amp. One important thing to keep in mind is that almost all current probes are active devices. That is, they require power to operate. All current probes can detect and measure alternating current, but some are also able to measure direct current as well. Different mechanisms are used for each type of measurement. AC measurements are made using a current transformer. On the other hand, DC, or very low-frequency AC measurements, are made using something called a Hall effect sensor. Probes that measure down to DC use a combination of these two methods. Note that Hall effect sensors are active devices, that is, they require a power source, and this is why AC-DC probes are usually active devices. There are several considerations when selecting a current probe, the first of which is AC only or AC-DC operation, as just discussed. Another important consideration is bandwidth, or the frequency range over which current can be accurately measured. This is usually about 100 MHz or less. Probes which are AC only will also have a lower bandwidth limit. Since current probes produce a voltage that's proportional to the measured current, the gain, sensitivity, or scaling factor of the probe is also important. This is specified in volts per amp, that is, how many volts are produced per ampere of measured current. Some current probes also come with a physical switch that allows this scaling to be changed. The maximum voltage and current and the CAT rating of the probe limit the maximum measurement value, and these can also be important for safety considerations. And finally, current probes also differ in the way that they connect to the scope. Let's look at this in a bit more detail. Current probes may attach to the scope through a proprietary interface or using a standard BNC connector. The advantages of using a proprietary interface are that this enables the scope to provide power to the probe, and this also enables the scope to sense the probe type, thereby allowing it to automatically set the proper scaling factor. Degaussing and zeroing, topics we'll discuss in a few moments, can also be performed via the scope's interface. On the other hand, current probes with a standard BNC interface can be used with any oscilloscope. They have external physical controls for degauss and zeroing, but require an external power source. This can be a USB connection, an internal battery, or a proprietary external supply or connection. Using a clamping-style current probe is very simple. The clamp or jaws are opened and then closed around the conductor. Using these types of clamping or split-core probes has the advantage that the circuit does not need to be broken. Current probes normally have a direction of current marker or label. This arrow is used to indicate the direction of conventional, that is, plus to minus, current flow in the measured conductor. Current probes will still work if they're connected backwards, but the sign of the measured current will be reversed. Current measurement sensitivity can be increased by looping the conductor through the probe multiple times. The sensitivity of the probe increases linearly with the number of loops. Looping the conductor through the opening 4 times improves sensitivity by a factor of 4. Since the scope has no way to know how many times the conductor has been looped, an appropriate scaling value must be manually entered into the scope. These loops also increase the insertion impedance by the square of the number of loops, so 4 loops would increase the insertion impedance by a factor of 16. However, this increased insertion impedance is usually still quite small and does not significantly affect measurements at low current levels. Ideally, a current probe should show a 0 ampere current rating when no current is present, but due to temperature and other environmental considerations, the 0 value of a current probe may change over time. This can, and should, be corrected using something called zero adjustment or zeroing. There are 2 different ways to zero a current probe. For probes with a non-proprietary interface, a zero offset knob or wheel is usually built into the probe itself. We'll see an illustration of this on the next slide. Probes with a proprietary interface usually allow zeroing to be performed using the scope menu or controls. And some scopes even have an auto-zero function, which will apply the correct offset and direction automatically. For best accuracy, it's always a good idea to zero current probes before making any current measurements. Another potential issue when using current probes is that the ferromagnetic core of the probe may retain some of its magnetism or flux, even when there's no current present. This is not uncommon after a probe has been used to measure a current that was being switched on and off. This residual magnetism can lead to the creation of an offset, and thereby impact measurement results. Most current probes support a demagnetizing or degauss function that can be launched either from the probe itself or via the scope's user interface. A special waveform is generated such that it creates an essentially random magnetic field that erases any residual magnetism in the probe. This is normally a very quick process that only takes a few seconds. Therefore, whenever using current probes, it's a good idea to demagnetize or degauss the probe, both before zeroing as well as before making any measurements. Next, we'll discuss something called Deskew. Current probes are often used together with voltage probes when making power measurements, since power measurements require simultaneous measurement of both voltage and current. In some cases, a time offset or skew may exist between measured voltage and measured current waveforms. This is primarily due to different propagation times in the probe leads, and this skew can lead to incorrect power results. Special deskew fixtures are used to detect and compensate for skew by generating time-aligned voltage and current pulses. These pulses are simultaneously measured by attached current and voltage probes. If these test waveforms are skewed, an appropriate deskew or time offset value can be entered on the scope to bring the current and voltage waveforms back into phase and improve the accuracy of power measurements. In addition to single-ended passive probes and current probes, another very important type of probe is differential probes, so we'll discuss these in detail in the next section of this presentation. To understand differential probes, we need to review what we mean by a single-ended measurement. Recall that standard passive probes commonly used with oscilloscopes are single-ended, in that they measure voltage between the probe tip and ground. As we saw in the section on passive probes, a special ground lead is used for this ground connection. This is commonly a wire with an attached alligator-style clip. In most cases, this ground lead is electrically connected to the electrical or chassis ground of the scope, and this ground is also shared across all oscilloscope channels. It's very important to remember that when this ground lead is attached to a point in a circuit, that point in the circuit is forced to ground. One potentially undesirable consequence is that excessive current can flow through this ground connection, leading to incorrect results and damage to the circuit and/or damage to the scope. At high enough current levels, this unintentional connection to ground can even be a safety hazard to the human operator of an oscilloscope. It is, however, sometimes necessary to measure voltage between 2 points where neither point is ground, and this is referred to as a differential measurement. One very common application of differential measurements is measuring the high voltages across power transistors. Another very common application is measuring differential signals, such as USB, CAN, etc. Differential signaling, or encoding, conveys information by using the difference between 2 voltages, and thus has a much higher immunity to noise than single-ended signals. One additional area where differential measurements are useful is where a nominal ground exists, but is noisy or unstable. There are 2 ways to measure differential voltages. The first is using a pair of single-ended probes. This is often referred to as the quasi-differential approach. The second method is using special differential probes that are specifically designed to make differential measurements. Let's start by looking at the quasi-differential method. In the quasi-differential method, 2 single-ended probes are used to acquire the high and low voltage sides of a signal. The scope's math function is then used to subtract one channel from another in order to obtain the differential voltage between the points. The biggest advantage of this method is that common passive probes can often be used, although this also means that 2 scope channels are required for each differential measurement. For best accuracy, it's also important that the probes be well matched. That is, both probes should be the same type and model, they should have the same cable or path lengths, and the ground lead length and ground connection should also be the same for both probes. But the preferred way of making differential measurements is using a differential probe. This type of probe has 2 inputs that can be connected anywhere in the circuit, and neither of these points needs to be ground. Differential probes are constructed using an internal differential amplifier and produce an output voltage that corresponds to the difference between the 2 measurement points. This voltage is normally scaled by a known or selectable attenuation factor. Ideally, a differential probe would not respond to so-called common mode signals, that is, signals that are identically present at both measurement points. This makes differential probes a good choice when measuring low-level signals in the presence of noise. And finally, a differential probe can be used to make a single-ended measurement simply by connecting one of the leads to ground. Let's pause here for a moment to discuss why differential probe leads are often twisted together. Differential probe leads should be kept as short as possible to reduce the pickup of common mode noise, but most differential probes come with rather long leads. These leads are often twisted together to help minimize the pickup of external noise. This twisting of the leads does, however, increase the capacitive loading of the probe, and therefore the leads of a differential probe should be left untwisted if it's important to keep the probe's capacitive loading to a minimum. There are both advantages and disadvantages to using differential probes. The advantages include that only a single oscilloscope channel is required for the measurement. Recall that the quasi-differential approach required 2 probes, and therefore 2 scope channels. And as mentioned earlier, differential probes can also be used for both differential as well as single-ended measurements. Differential probes are safer for both devices and humans, especially in high-voltage environments. And differential probes also have a higher common mode rejection ratio, something we'll discuss in detail in just a few moments. Some of the disadvantages of differential probes are that they're considerably more expensive than passive single-ended probes, and they also tend to be physically larger. Also, due to the differential amplifier used to compare the voltages, differential probes are active, that is, they require power, either from the scope itself or from an external supply or internal battery. In addition to the typical probe specifications such as bandwidth and attenuation, there are three special considerations when using differential probes. These are common mode rejection ratio, differential mode range, and common mode range. Before we conclude this section on differential probes, let's take a brief look at each of these specifications. As mentioned earlier, an ideal differential amplifier should reject or suppress non-differential or common mode signals that appear identically on both amplifier inputs. In practice, these common mode signals are usually noise or an offset. The ability to reject common mode signals is quantified as the common mode rejection ratio, or CMRR, and it's defined as the ratio of differential mode gain to common mode gain. Since the ideal common mode gain is 0, the ideal CMRR is infinite, but most differential probes have a CMRR of about 30 to 80 dB, with higher values being more desirable. Note too that CMRR normally degrades as frequency increases. One of the advantages of differential probes is that they have a much higher CMRR than can be achieved using the quasi-differential approach. And this is another reason why differential probes are preferred over the quasi-differential method. A related specification is differential mode range, which is the maximum allowable voltage between the two probe or amplifier inputs. This value is generally symmetric with polarity. That is, it's the same from plus to minus and from minus to plus. Because it's important to know the maximum measurable differential voltage, this value is usually printed directly on the probe body itself. Note that this value also depends on the probe's attenuation settings. Here, if the differential probe attenuation is set to 20, DMR is only 140 volts. But DMR increases to 1400 volts when attenuation is increased to 200. It's usually easy to detect when DMR is being exceeded, since the differential signal is what's being displayed on the oscilloscope. Typical signs of exceeding the maximum range are clipping or distortion of the measured signal. In addition, some modern differential probes will also have a visual overrange indicator on the probe body itself, or will produce an audible signal or beep when maximum voltage is exceeded. The third special differential probe parameter we'll look at is common mode range, which is the maximum voltage between each individual probe input and ground. Like DMR, this value is usually symmetrical. And like DMR, this is also often printed directly on the probe itself. Note, however, that unlike DMR, CMR does not change with input attenuation. It can, however, be difficult to know if the common mode range is being exceeded, since the voltage between a single input and ground is not directly seen on the scope. Momentarily disabling one input and connecting it to ground is one way to detect when CMR is being exceeded. And, as in the case of DMR, some modern differential probes will have a visual indicator on the probe body itself, which shows when the common mode range is being exceeded on one or both inputs. The last of the oscilloscope probe types we'll discuss in this presentation are so-called active probes. It would probably be best to start by explaining what we mean by an active probe. Generally speaking, active means that the probe requires power. Recall that passive probes do not require a power source. Using this definition, differential probes and most types of current probes are also active probes, since these two types of probes also normally require power. However, for most oscilloscope users, the term active probe refers more narrowly to a single-ended FET probe. And in the remainder of this presentation, we'll also use the term active probe to refer to this specific type of probe. The amplifier in the tip of an active probe means that it has much lower input capacitance than passive probes. This lower capacitance has two major advantages. The first is reduced circuit loading, which allows for a more faithful reproduction of the measured signal on the scope, and a lower impact on circuit operation. The other is higher bandwidth, which is needed for more accurate measurement of higher speed signals, and in particular, signals with higher frequency components. In addition, some active probes can also apply a relatively large offset to the signal, which is very useful when trying to measure small AC signals on top of larger DC signals. A good example of this is power supply ripple. Active probes are therefore an excellent choice for many demanding measurement applications. Active probes normally require that the scope channel input impedance be set to 50 ohms, and these probes also normally obtain their power from and are controlled by the oscilloscope. For these reasons, active probes are generally manufacturer-specific. That is, you can't normally use one manufacturer's active probe with another manufacturer's scope. That said, in some cases a special adapter can be used to interface with a different manufacturer's active probes. It's also worth noting that active probes can also sometimes be used with instruments other than oscilloscopes. For example, some spectrum analyzers may support the attachment and use of active probes for making frequency domain measurements. On a previous slide, we briefly touched on the three important characteristics of an active probe, namely loading, bandwidth, and offset range. Active probes have significant advantages over passive probes in all three of these areas, so let's take a few moments to explain each of these in more detail. Recall that one of the advantages of active probes is they can reduce circuit loading, because the amplifier in the tip of an active probe enables active probes to have very low input capacitance. Traditional passive probes have input capacitances in the range of tens of picofarads, while the capacitance in active probes is commonly single-digit picofarads or less. This lower input capacitance means the probe has a higher input impedance, and therefore lower circuit loading. For example, the amount of ringing seen on a square wave signal is significantly higher with passive probes than with active probes. This is especially true at higher frequencies. Active probes are therefore often a better choice when connecting to high impedance circuits that would be significantly loaded by using passive probes. Another advantage of active probes is that, on average, they have a much higher bandwidth than passive probes. While most passive probes have bandwidths in the tens or hundreds of megahertz, active probes often have bandwidths well into the gigahertz range. The bandwidth of any probe is related to that probe's loading. Remember that loading will increase rapidly at high frequencies if a probe has a high input capacitance, and as we've mentioned earlier, the design of active probes gives them a low input capacitance, and thus lower loading at high frequencies. Therefore, active probes are recommended for signals that are high frequency and for signals that have fast rise times or significant harmonic content, such as square or pulse signals. Before we go on, let's pause for a moment to discuss offset range in oscilloscopes. A good general rule when using an oscilloscope is that the signal of interest should be both vertically centered in the display, as well as fill most of the screen. This maximizes the use of the scope's ADC, or analog to digital converter. It can, however, be challenging for signals with a small AC component riding on top of a large DC offset. For example, when measuring the amount of ripple on the output of a DC power supply. One solution is to enable AC coupling on the channel in order to remove or block the DC component. But this also removes the ability to see drift, etc. Another approach is to apply an offset to the channel so as to vertically center the signal. After this offset has been applied and the signal has been moved to the center of the display, the volts per division setting can be decreased to see the AC component of the signal in more detail. An important limitation to this approach is that the maximum offset range is limited by the vertical scale setting. Small volts per division settings reduce the maximum configurable offset range. How does this apply to active probes? Many active probes have the ability to apply an offset within the probe itself. This offset is separate from, or in addition to, the offset range in the scope, and is also independent of the scope's volts per division setting. This means that probe offset can be used to vertically center signals in cases where the scope offset is insufficient. Because probe offset is not limited by the volts per division setting, using probe offset often enables greater vertical sensitivity when looking at signals with large offsets. This in turn improves the achievable vertical resolution and the ability to see or measure smaller signal details. Let's end with a brief summary. Probes are the interface between an oscilloscope and the measured signal. The type and characteristics of a probe will affect not only the measurement, but the probe can also load or otherwise affect the circuit under test as well. There are many different types of oscilloscope probes, and in this presentation we've covered the four most important ones. The first is basic passive probes, which are by far the most common and which are normally included when purchasing an oscilloscope. These basic probes can be used for a wide range of measurement tasks, but it's important to remember that these probes should be properly compensated before being used. Current probes are a special type of probe which allows an oscilloscope to measure current instead of voltage. A current probe converts the measured current into a voltage that the scope can then measure and process. Differential probes are used to measure voltage between any two arbitrary points in a circuit. This is different from single-ended passive probes, which are used to measure voltage with respect to ground. And finally, so-called active probes have an amplifier in the probe tip that provides numerous advantages, such as reducing circuit loading, increasing measurement bandwidth, and providing a high offset range. This concludes our presentation, Oscilloscope Probe Fundamentals. If you'd like to learn more about oscilloscopes or probing, or about oscilloscopes and probes from Rohde and Schwarz, please see the links in the video description. Thanks for watching.